We'll begin our determination of reaction order and rate constants by considering unimolecular reactions. So let me establish that up here. And in particular, what I want to do is take a look at the time dependence of a concentration of the reactant A and compare it to integrated rate laws. Now, I'll remind you that at the beginning of an experiment, we do not know the rate law. So we do not know its order, we do not know its rate constant. I will also indicate that when we make these experimental measurements, we're typically going to be subject to random fluctuations in the data. Now, these fluctuations aren't necessarily very large, but it does mean that the points that we measure off of an experiment aren't going to lie precisely on some curve or on some mathematical function. So this is going to affect the precision with which we can determine certain values. And in general, I would say that the rate constant is usually only established within 2, possibly 3 significant figures, but 2 is probably about as much as you're going to get in many cases. Finally, we're going to use this as a method for comparison with theory. Okay, so that means we have to be aware of the models that we want to compare it to so that we can see how well the experiment fits those models. And the model that it fits the best is going to be the one that we will adopt as being representative of the rate for that particular reaction. All right, now how do we do this? I'll say that generally speaking, when we want to try to compare an experimental set of data with a theory, the theory is going to predict some sort of functional dependence, some sort of curve. And the experimental data, of course, may look like that curve, or it may not, depending on the fluctuations in the data itself. So the easiest way to typically compare experiments with a theoretical curve is if the theoretical curve is a line. So we're going to be looking for something that will enable us to plot our data as a linear plot, that is, as a line plot, so that we can use regression analysis to study it. Now, a couple of reasons for using regression analysis. One, it's a very well-developed theory, so we know lots of different ways that it can be tweaked and it can be probed in order to get useful information. But the second is that there are many, many ways, many places online that you can go to do a linear regression analysis. So you really don't have to reinvent the wheel here. It's something where there are readily available programs that you can use to do a linear regression fit. Okay, so what does this mean? Now we're doing a linear plot, so we're implicitly trying to fit our data to an equation that looks like this, where y and x are the two variables. X is the independent variable, y is the dependent variable, m is the slope of the line, and b is the y-intercept. All right, so that's what we're trying to do. Now what I want to do is lay out the different orders of reaction that we could possibly have for a unimolecular reaction, and then see what sort of thing we would need to plot in order to make a useful comparison. So let's start with order equals 0. This is, of course, the simplest possibility, and it's also maybe the least occurring. Okay, in that case, you'll recall that the integrated rate law could be written like this. All right. Where here, what we're looking for is a way to arrange the data so that we have some function of the thing that we're measuring. Okay, in this case, this is what we're measuring. And we want to measure it versus t. So t is going to effectively be our x variable. So I want to put this especially up here. That's our x variable. And this is going to be related to our y variable. But the y variable may be some function of this. Now, as I've written this here, I can identify a as a function of time as y. I can identify t as x, so this is like mx, and this a at time 0 is b. So in fact, I already have this in a linear format. So if I were to plot the data for this, I would simply have to plot the concentration of A as a function of time, like this, and it will be a bunch of points, and I shouldn't make them look too curvy. It'll be a bunch of points like that, and the best fit line through those points will be the thing that I get from a data regression analysis, a linear regression analysis. Now, I'll note that in this plot, a couple of things. One, the slope. What is the slope in this case of this line? Because that's important information. Well, in the case of y equals mx plus b, m plays the role of the slope. And in this case, m is associated with minus k. So in other words, this slope is equal to minus k in this plot. The y-intercept up here is simply going to be b, so the y-intercept is simply the initial concentration of A. Now we usually know that to begin with, so maybe this is one way to check and make sure that your linear regression analysis is doing the right thing, because it should give you a value pretty close to the value you know to be the initial concentration of A. But it's a fairly simple prospect for zeroth order reactions, and so for that reason I might say that it's a fairly uninteresting case. All right, what would be more interesting is when we have order equal to 1. So let me put this here, order equal to 1. And we know that, for example, the time dependence of A is equal to its initial value times e to the minus kt. All right, we no longer have a nice arrangement as we did over here in the case of the zeroth order reaction. This does not look like a line at all. In fact, we know from a vast experience that this function here is a decaying exponential. It looks something like this. So it's not a line. How can we make this into a line that would be useful to do a linear regression analysis? Well, the most straightforward way is to take the natural log of both sides of this equation. When we do that, we'll end up with an equation that looks like this. Log of A at time t is equal to log of A at time 0 minus kt. Okay, now when we do this, once again, we can identify t as being our x-coordinate. Log of A is going to be our y-coordinate. Minus k is our slope. And log of A at time 0 is our y-intercept. So now when I make a plot of this data, I'm not plotting just the concentration versus time. Now I'm plotting the logarithm of the concentration as a function of time. And again, I'm going to get a scatter of points that roughly follow a line. The line will go through those points. We'll find the best line through them. And again, the slope is one that we can associate with minus k. Okay, so we're directly getting the rate constant from measuring this slope. The y-intercept in this case is simply going to be the log of A at time 0. All right, so again, this is a number that you should probably know in advance because you know what your initial concentration was. So this is a good way of verifying that your linear regression analysis is fairly accurate. Okay, finally, what do we do when we have a second order equation? So let's put this over here on the far right. Order equals 2. Okay, in this case, we know that 1 over the concentration at time t is equal to 1 over the initial concentration plus kt. Now, we want t to be our x-coordinate, and we can see that this is already in a format that looks pretty linear. Again, this case, the slope would be plus k instead of minus k, so it's a little bit different from these others. Okay, but this function that we're graphing over here, which I'll associate with the y-coordinate, is 1 over the concentration. So in effect, what we're doing is we're graphing 1 over A versus kt. So let's see what this looks like. So once again, we'll draw our graph, function of temperature, and now this axis up here is graphing 1 over the concentration, and now the slope is going to be a positive slope, so we'll have a bunch of points going up like this and a line that goes through them. And when we begin to do our analysis, we would find that this line has slope that's equal to plus k. And the intercept down here is going to be 1 over the initial concentration of A. All right, so in effect, what we have here are prescriptions for manipulating the data that we get from the experiment so that we can compare it against a line. We can basically use a linear regression analysis to fit a line to that data and then use that line to tell us the values of the things that we want to know, particularly the rate constant. Now, I should note that since we don't know the order in advance, what we end up doing in practice is we have to do each one of these plots and see which one fits better. Okay, so we have to plot, in this case we're plotting the concentration versus time. In this case we're plotting log of the concentration versus time, and in this case we're plotting 1 over the concentration versus time. But the process that we're following is that we're measuring the concentration at different times. We're then constructing these graphs for each of the orders that we need and performing the linear regression analysis. What we get from linear regression, and I should probably lay this out, we get 3 pieces of key information. You actually get more information than that, but I'm going to identify 3. We get the slope, and we know that this is related to the rate constant. We get the intercept, and this is perhaps less informative for us because it's related to the initial concentration of our reactant. But the third thing we get is very interesting and very important, and that is something called the coefficient of determination. Now, what the heck is that? Okay, it's usually labeled R squared. And what this is it tells us how well does our data actually lay on a line. And the closer this is to 1, so I'll just say 1 means good, and anything away from 1, so not 1, is bad fit. Now what you'll have when you, for example, take a set of data and you'll massage the data to make these 3 plots and you'll do the linear regression analysis, is you'll get a value for R squared that is different in each case. So you look for the one that is going to be closest to 1, because that's the one that's it's telling you that's the one for which the linear regression creates the best fit for your particular data. So it helps you to identify from that which one of these plots is going to be the right one, and the plot that it's identified tells you the order of the reaction. That also tells you from which plot you read off something like the value of the slope so that you can get the rate constant, because you'll get 3 different values for the rate constant on the same set of data by making each of these plots. All right, so this has been a crash course in linear regression analysis. I'll simply mention that you can do a linear regression analysis using Excel spreadsheets. They've got the functions in there. Use the slope and the intercept function, for example, to get that best fit line. But an even better way, I think, is using Wolfram Alpha. And if you use the function linear fit, and you'll probably need to look that up in Wolfram Alpha, use linear fit, it will give you the slope, it'll give you actually an equation of the line, it will give you this coefficient of determination so that you'll know which one is the best fit. And it'll actually give you a plot of the line with your data, which can often be helpful to see as well.